Namaste dear students, I am B.G.Shinde sir and we are discussing chapter number 3, Kinetic Theory of Gases and Radiation of 12th Standard Physics. Today we start lecture number 15 and its topic is Wein's Displacement Law and Stefan's Boltzmann Law of Radiation. In last lecture number 14, we have studied the spectral distribution of the perfectly black body. Means we have drawn one graph of the spectral distribution of the perfectly black body. In that graph, we have seen that there is a wavelength along x-axis and radiant power along y-axis, and this is the nature of the graph we have studied. This is the nature of the graph, and in this graph it is very clear that this lambda corresponding to the maximum radiant power, and the value of the lambda which is corresponding to maximum radiant power will go on decreasing. Means it goes on, it is shifted toward the left, it goes on decreasing as there is increase of the temperature. As there is increase of temperature, there is a decrease in the value of lambda max, and this is called the Wein's displacement law. So what is Wein's displacement law? According to Wein's displacement law, the wavelength corresponding to the maximum emissive power is inversely proportional to the absolute temperature of the perfectly black body, and this is called the Wein's displacement law. So we can write lambda max inversely proportional to T. This is called Wein's displacement law. Lambda max inversely proportional to T, or we can write lambda max equal to some constant upon T, and this constant B is a Wein's constant and its value is 2.897 into 10 raised to minus 3 meter degree Kelvin. So this is the formula of the Wein's displacement law. According to Wein's displacement law, the wavelength corresponding to maximum emissive power is inversely proportional to absolute temperature of the perfectly black body, means lambda max proportional to 1 upon T and lambda max equal to B upon T, where this B is called the Wein's constant and its value is 2.897 into 10 raised to minus 3 meter degree Kelvin. This is the Wein's displacement law. Now this maximum wavelength indicate that the lambda max or that wavelength will be dominant there in that spectrum or in that radiation. Maximum of the wavelength will be lambda max. All the wavelength will be lambda max, or it will be most of the wavelengths will be lambda max in that radiation. And for that purpose, this white drops म्हणजे त्याला मराठीत आपण बटू तारे म्हणतो. बटू तारे की जे ज्यांचा प्रकाश हा कमी असतो, तर हे जे बटू तारे असतात त्याला व्हाईट ड्रॉप्स म्हणायचं. तर हे जे पांढरे जे बटू तारे आहेत, तर यांचं जे टेम्परेचर असतं ते 1000 डिग्री केल्विन असतं. आणि त्यांच्यामधून लॅम्बडा मॅक्स जे जास्तीत जास्त जी वेवलेंथ जी त्याच्यातून ती बाहेर पडणारी असेल लॅम्बडा मॅक्स, त्याच्यामुळे त्यांचा जो कलर असेल तो त्या पद्धतीने व्हाईट येतो. सिमिलरली रेड जायंट जे आहे हा सुद्धा एक तारा आहे. रेड जायंटचं टेम्परेचर असतं 3000 डिग्री केल्विन आणि ह्या रेड जायंटचं टेम्परेचर 3000 आहे. त्याच्यातून जी डॉमिनंट जी वेवलेंथ असेल म्हणजे लॅम्बडा मॅक्स जी आहे ती, त्याच्यामुळे त्याचं ते जे आहे रेड जायंट त्याचा कलर हा रेड असतो. सो this Wien displacement law can be useful to determine the temperature of the star. म्हणजे एखादा स्टार आहे आणि त्या स्टार मधून येणारा कोणता जो लाईट असेल तो लाईटचा कलर जर आपण डिटेक्ट केला आणि तो कलर त्या कलरचे जे वेवलेंथ जर आपण सबस्टिट्यूट केले तर आपल्याला तो जो स्टार असेल त्या स्टारचं टेम्परेचर सुद्धा फाइंड करता येतं. टेम्परेचर ऑफ द स्टार्स can be determined by using Wien's displacement law. So this is all about the Wien displacement law. Now we see what is the Stefan-Boltzmann law of radiation. Now according to this Stefan-Boltzmann law of radiation, this law Stefan-Boltzmann law was this law was first told by the scientist Stefan, and according to scientist Stefan, he has observed that radiant energy emitted per unit time per unit surface area is depend upon the fourth power of the absolute temperature. He observed that law. He observed this. He have made this observation. म्हणजे त्याने असं हा लॉ आधी तयार केला. नंतर 5 वर्षांनी बोल्ट्झमन नावाच्या सायंटिस्टने थर्मोडायनामिक्सचा यूज करून सेम लॉ व्हेरीफाय केला. एक्सपेरिमेंटली सेम लॉ थर्मोडायनामिक्सचा यूज करून तयार केला आणि म्हणून हा जो लॉ आहे याला स्टीफन-बोल्ट्झमन लॉ ऑफ रेडिएशन असं म्हटलेलं आहे. इट इज कॉल्ड स्टीफन-बोल्ट्झमन लॉ ऑफ रेडिएशन. 2 सायंटिस्टचं नाव त्याला दिलेलं आहे. नाउ व्हॉट इज स्टीफन-बोल्ट्झमन लॉ? अकॉर्डिंग टू स्टीफन-बोल्ट्झमन लॉ, रेट ऑफ इमिशन पर युनिट एरिया is per unit area of the perfectly black body is directly proportional to the fourth power of the absolute temperature. This is the law. What is the law? The rate of emission per unit area of the perfectly black body or radiant power per unit area of the perfectly black body is directly proportional to the fourth power of the absolute temperature. So you can write this law as R proportional to T raised to 4. So R means it is a radiant power and it is directly proportional to the fourth power of the absolute temperature. Or you can also say that the radiant energy emitted per unit time per unit surface area of a given body at a given temperature is directly proportional to the fourth power of its absolute temperature. So this is the statement of the Stefan-Boltzmann law of radiation. So R proportional to T raised to 4. So you can write R equal to sigma T raised to 4. Now what is sigma? Sigma is a constant. It is called the Stefan's constant, and it is 5.67 joule per second per meter square degree Kelvin raised to 4, or 5.67 watt per meter square degree Kelvin raised to 4. So this is the statement of the Stefan-Boltzmann law. So rate of emission of a perfectly black body per unit area is directly proportional to the 4th power of its absolute temperature. This is the law which is called the Stefan-Boltzmann law. Now suppose you take an ordinary body instead of the perfectly black body. If you take ordinary body, then for ordinary body this R will be equal to E sigma T raised to 4. This is for perfectly black body. Means R be equal to sigma T raised to 4. This is for perfectly black body. And for ordinary body it will be R equal to E sigma T raised to 4. Now why we take here E? This E is called the emissivity, and emissivity E is equal to R upon RB. This is the formula, this is the definition of emissivity. The ratio of the emissive power of the ordinary body and the emissive power of the perfectly black body, it is E. And therefore for ordinary body R is equal to E into RB. Ordinary body साठी हे E into RB असेल. मग RB ची किंमत असेल सिग्मा into T raised to 4. आणि म्हणून ordinary body साठी R ची किंमत राहील R equal to E sigma T raised to 4. Now suppose that we take a body of temperature T and it is kept in the surrounding of temperature T0. Then the amount of heat which is or the radiant amount of heat emitted per unit time per unit surface area from that body, from that perfectly black body will be equal to R equal to sigma into T raised to 4. Means this is the radiant energy emitted per unit time per unit surface area of the perfectly black body. And since this body is kept in the surrounding of temperature T0, the radiant energy which is absorbed by the surrounding will be sigma into T0 raised to 4. म्हणजे जर समजा एखाद्या बॉडीचं टेम्परेचर जास्त आहे आणि सराउंडिंगचं टेम्परेचर कमी आहे, तर बॉडीकडून सराउंडिंगला हीट लॉस केली जाईल. म्हणजे टेम्परेचर म्हणजे की हीट जे असेल हीट सराउंडिंगकडून ॲब्सॉर्ब केली जाईल. तर एवढी हीट त्या सराउंडिंगने ॲब्सॉर्ब केलेली असेल. अँड देअरफॉर नेट लॉस ऑफ हीट of the by the perfectly black body will be equal to sigma T raised to 4 minus sigma T0 raised to 4 equal to sigma T raised to 4 minus T0 raised to 4. So this is the net loss of the heat by perfectly black body when it is kept in the surrounding of temperature T0. If you take ordinary body, then net loss of the heat will be E sigma T raised to 4 minus T0 raised to 4. म्हणजे जर ऑर्डिनरी बॉडी असेल तर E घ्यायचा स्मॉल e into sigma T raised to 4 minus T0 raised to 4. Then suppose that temperature of surrounding means T0 is greater than temperature of the body. T0 is greater than temperature of the body T. Then there will be net gain of the heat by the body, and net gain will be equal to sigma T0 raised to 4 minus T raised to 4. So this is net gain of the heat by the body. So this is all about the today's lecture, and that is end of the theory part of this chapter. Thank you very much.